Thank you for joining us today. My name is Julia Masterman. I'm the Education and Outreach Specialist for CUAHSI. And today we have the final panel in this series on digital hydroconnectivity. Before we kick things off and I pass it on to our speakers and conveners, a couple things that I'd like to note. Firstly, this has been an incredible series of talks that have been going on since the beginning of November. This is our final talk in the series, but the previous ones can be found on the CUAHSI YouTube channel. So if you haven't been here previously and this discussion sparks some interest, definitely feel free to check those out there. A couple things about CUAHSI as folks are getting connected and settled. CUAHSI's mission is to shape the future of water science by strengthening multidisciplinary collaboration, providing critical infrastructure through our data services, and promoting education in water science at all levels, in part through programs like this Cyberseminar series. We seek to achieve this mission in two main ways, through our community services and our data services. Our community services include things like grants and fellowships, workshops and trainings, the National Water Center Summer Institute, the virtual university, and hydrology guest lecture database, and more. Feel free to check our website for more information on all of these or reach out to me. I'll put more information in the chat in a moment. A couple upcoming deadlines. CUAHSI is accepting training workshop proposals for a couple more days. If there's a specialized topic or method that you'd like to share with a broader audience, CUAHSI can assist in hosting a training workshop. So if you have any questions about that, please feel free to reach out to me or check out our website for more information on previous workshops that have been hosted. We also have some funding opportunities coming up. The Hydroinformatics Fellowship just closed their application deadline, and we look forward to seeing the outcome, more incredible outcomes from that fellowship. And the Pathfinder Graduate Student Fellowship is currently accepting proposals. The deadline for that is coming up at the end of December. The other side of our organization are our data services. CUAHSI provides tools and support to enable all aspects of the data lifecycle from discovery to publication, in part through our two main data repositories, HydroShare and HydroClient, or HIS. This is very brief, but again, please feel free to contact us, sign up for our newsletter, and visit our website. I'll put links for all of those in the chat in a moment. But before we get started today, a few logistics. This webinar is being recorded and will be posted on the CUAHSI YouTube channel later this afternoon. Secondly, we ask that you use the Q&A functionality to submit any questions to our panelists. We're looking forward to an engaging discussion with input from all of you. Finally, we expect that all involved with CUAHSI Cyberseminars promote and maintain a professional, considerate, respectful, and collaborative virtual environment. So thank you for being a part of that. Thank you again for joining us. And I would like to pass the mic to this series, the convener, one of the conveners for this series, Sudarshana Mukhopadhyay, who will be moderating the session. Thank you very much.
Thank you, Julia, for that introduction. First of all, thank you all for joining us today. As Julia mentioned, we will be monitoring the Q&A section throughout the seminar and save all questions for the end. So today in our panel, we have 4 speakers. And after their opening remarks, we will open the virtual floor for discussion. Our first speaker is Dr. Jerad Bales. He is the Executive Director at CUAHSI, and he develops and implements the overall strategy for CUAHSI. And before this, he has worked with the USGS for 25 years in different leadership roles. So without further ado, I'll turn it over to Jerad.
Thank you. Thank you all for joining. So most computational hydrology is not reproducible. So is it really science? That's the title of a paper that was published in 2015 and in Water Resources Research, and we still struggle with reproducibility. In fact, science should be repeatable. The same team doing the same experimental setup gets the same result. Science should be replicable. A different team using the same setup gets the same result, and it should be reproducible. A different team using a different setup gets the same result. And so this is not just kind of an esoteric ideal. If you remember in early 2020, at the beginning of the pandemic, there were multiple models being published, and results of those models were being used to kind of guide the response of the healthcare community. But these models were not open source. The forecasts differed widely, and there was really very little confidence in those models, I think, by the public for these reasons. There was a commentary published in Science pointing this out, and now I believe most of the forecast models are on GitHub. You can go and see them, but still the current forecasts of deaths from COVID in the coming week differ by a factor of 2. So this ideal of reproducible science has kind of real world implications just beyond hydrology, for example. So CUAHSI focuses on fair data and fair workflows, especially reproducible workflows. In HydroShare, CUAHSI HydroShare, users can share and collaborate and publish data and workflows both. In the CUAHSI Hydrologic Information System, we offer 100 individual data services with over 1 billion data points. We've just added Bureau of Reclamation and California Department of Environmental Conservation data. And users can publish their data with the DOI in these platforms. And so that helps to make data fair, findable, accessible, interoperable, reproducible. CUAHSI is currently modernizing the hydrologic information system, which is about 10 years old, but was really one of the first implementation of sharing water data across multiple platforms. As a part of this upgrade, we will be involving or including things like GeoConnects that you heard about earlier, as well as Dendra for sensor streaming. So the progress toward the goal of findable, accessible, interoperable, reusable data has been slow, and is often focused on technical solutions, which kind of is what we're talking about today. But technical solutions also miss sort of a critical socialization aspect of fair data and workflows. There are misconceptions about fair data, about the costs and the benefits of data sharing, and confusion about how to do it. And so as a result, the societal benefits from data sharing are not really being realized. Within models that as hydrologic models, there are kind of 2 different kinds of workflows: model agnostic and model specific activities. Hydroconnectivity is a model agnostic type workflow and should be repeatable. These tools that we have learned about and that we'll hear about later on in this webinar help the community achieve the ideal of reproducible science. So thank you, and I look forward to your questions.
Thank you, Jerad, for your opening remarks. Our next speaker is Dr. Stacey Archfield. She is a research hydrologist at the USGS. Her research is focused on understanding the hydrologic change for water resources application, and she is an excellent and long-time collaborator also. So now I'll pass the mic to Dr. Archfield.
Oh, thanks so much for those comments. I appreciate it. So today I'm going to talk about the ongoing efforts within the USGS on hydrologic connectivity These comments have been pulled together by talking to my colleagues at the USGS, so it's certainly not representative of my own work. I just want to make that known, and I'll cite my colleagues when I can throughout this opening comments. Also, as you probably are all aware, the USGS does a lot of innovative work in our field offices, our water science centers that are located in every state in the United States. And so this is representative of some of the work going on, I would say, at the headquarters level. And so if there are USGS staff that are participants that I've missed highlighting your work on hydrologic connectivity, I would encourage you to put that in the chat today so that we can all be aware of that work as well. So really hydrologic connectivity, from kind of what I'm thinking of our USGS perspective, at least what's relevant to the work that I'm going to be talking about, which is dam location and kind of operation of dams, continues to be a critical data need for the USGS. And there's a number of programs that we have at the USGS. I'll give their names and then I'll explain what really the interest is we have two programs related to the modeling of water availability. And you may have heard their names, the Integrated Water Prediction Program. And then we have this Integrated Water Availability Assessment Program to really look at how we can map water availability and quantify water availability, quality and quantity across the United States. So of course, hydrologic connectivity, dam location, dam operation is critical to that. Our drought program, of course, it's important to understand dam location and connectivity related to understanding drought. Our EcoFlows program, certainly we need to understand hydrologic connectivity as it's related to meeting the ecological needs for water. And then we have a StreamStats program. StreamStats has been now a longstanding program that's highly usable to our cooperators, people on the ground, things like Department of Transportations or decision makers, even at the very local level, where you can point and click on a stream location anywhere they're built out state by state, this tool is. You can click on any stream location, a basin will be delineated for you, and stream flows or statistics of stream flow will be estimated for you at an ungauged location. Generally speaking, right now, those estimates are based on natural or unregulated flow, but there's great interest in having estimates of regulated flow, so flow influenced by dams or impervious surfaces. And so understanding what kind of regulation is existing in that location, in that defined catchment area, would be very important to that. So those are just some of the ways in which, of course, hydrologic connectivity is of interest to the USGS. And so what are some of the data sources that we use? So the USGS uses federally sourced data on dams, but we do not collect data on dams ourselves. So we use two main data sources that we have, and I just want to highlight them. I might be getting down in the weeds here a little bit, but I was thinking maybe there's people on the call that are interested in using data sets for dams, and I was kind of, when I was pulling this together, thinking I didn't know the details of two of these data sets, and so I wanted to explain them to you. So the first is the National Hydrologic Data Set. So this is the NHD. And the NHD has information on dams. This is a national data set that has unique identifiers for every stream reach, if you will, an address. And then every feature on this addressing site for every stream reach in the United States has unique addresses or unique identifiers for what might be on these stream reaches, including dams. And these dams on the NHD are large dams that come from the US Army Corps of Engineers. And these dams have storage capacities for these large dams over 2,400 acre feet were included. So in 2007, there were about 60,000 dams that were included in the National Hydrography data set. And that's the data set that the dams that exist in the NHD on that data set have not been updated since 2010. So it's kind of a static data set where the dam locations were ensured to be correct, they're correctly located on the correct stream, but there's been no update to that data set since 2010. Because there hasn't been any large dam construction, generally speaking, in the United States, it's considered to be generally updated data set, but it's important to note that if you're using the dam information that's in the NHD, it hasn't been updated. But since 2007, there's been a lot that's happened in the federal geospatial data coordination world, and there's legislation that's been happening and coordination that's being required now. And we now have a coordinator, the National Hydrography Management and Planning Lead at the USGS, is named Becky Anderson. And Becky helps coordinate is our representative, I should say, for the National Geospatial Data Asset under the Federal Geographic Data Committee. So I know there's a lot of acronyms, and I can post all this information if you need it. But essentially what this means is that we needed more coordination at the federal level for all of these federal data sets. And so having different places where different federal data sets were being stored, for example, for dams, is probably not the best way to do things and the best use of taxpayer money. So a decision was made to avoid duplication, to have dams stored under the National Inventory of Dams. And so that is where currently the most updated locations of dams are for the United States. This is now, it was a private database for security reasons. Now it's a publicly available database, but this is the most up-to-date data set with the last, that's continuing to be updated. And so that's the data set you would essentially wanting to be used if you were looking for the most updated data set of dams, which would be the NID, the National Inventory of Dams. That leads to some confusion now within the USGS, even in our space, about whether we have some disorganization now about whether we should be using products with the NHD or the NID. And so that's actually kind of where we're at right now. This is really not to show you how, oh, the USGS doesn't have our stuff together. It's really to show you there's a lot of opportunities still that exist within even just coordination amongst hydrologic connectivity and data sets, even at the data level. I don't think it's a surprise to anyone who's worked with these data sets to know that there's still so much opportunity available with respect to this type of information. And so right now, what we're trying to do, we meaning USGS, and I'll say even more specifically, we, Dave Blodgett is a research hydrographer with the USGS, and Mike Johnson, who is a NOAA affiliate and data scientist for the Urban Flooding Open Knowledge Network, are working on a repository in the Internet of Water to try to link unique IDs in the NID to the NHD. So that way there doesn't need to be a duplication anymore of dams in each data set, that you can just simply use the NID to kind of upload that and link that to the NHD. So we're trying to kind of work on we'll just stop using that word. So we're just basically trying to work on figuring out how we can get these data sets linked together so that we don't have to have two different data sets floating around and one is not being updated and the other one is, because that leads to kind of confusion in the community, not just kind of, but it does. I'll add just one other effort that we have at the USGS available, and you can Google this as well. I can drop links into the chat after I'm done, but there's this other tool called USGS Hydrolink that contains a national anthropogenic data set, the waterfalls of the United States, and also a tool for calculating how far up the reach a feature is from your location. And this is developed by Daniel Wyfrick at the USGS Core Science Systems. And so this is also another tool that may be available to you in a point and click system to kind of give you some information about hydrologic connectivity that's more ecologically based data set, but also has information about connectivity. I just want to add one more comment to this. Is all of this is, I think, useful information, but one of the huge gaps we still have is with small dams and their effect on hydrologic connectivity. This is also a particularly pressing issue because, as I said, it's the largest knowledge gap and also contains the most uncertainty on effects in water availability. So there's many of these dams across the United States. And so automated procedures to try to figure out if these dams are appropriately mapped to the correct stream reach may prove difficult when trying to do that. Because there's so many of these dams, it would take, hundreds of hours, if not thousands, to try to go through individually and make sure, every one of these tiny dams is not only mapped, but then mapped to the correct stream in some type of network like an NHD type hydrographic data set. And then there's difficulties in estimating the management properties or behaviors of these structures too. It's difficult enough to understand how large dams are managed, but to understand even how these small dams behave in a modeling framework of some kind is also a huge gap and opportunity as well in a modeling framework. So all of this represents, a unique time at the USGS for this work, but I think a really unique time in the hydrologic community to look at really how regulation affects the water budget and water availability. With that, I'll stop. Thank you.
Thank you, Stacey, for the introduction. So our next speaker is Dr. Jamin Kai. He's a professor of Water Resources in the Department of Civil Engineering at the University of Illinois Urbana-Champaign. His research is focused on energy, water, environment sustainability, and sustainable and resilient infrastructure systems, to name a few. So without further ado, I'll turn it over to Dr. Kai.
Thank you. Good afternoon. Thank you for including me in the panelists. Reservoirs and dams, they alter the hydrologic regions, and they basically add anthropogenic collectivity to natural rivers network. So today I will share with you about the idea of how we could add reservoir component to a regional or national hydrological model. I know this is this is kind of an effort which has been undertaken for a while. So you might notice that there from the SWOT model group, soil and water assessment tool, and they tried a few things recently. So a simple approach is to add some simple rules to their decision table, and then based on different conditions, they can check what kind of release should be taken. And recently, they also developed some data-based operation functions for different operation zones for like a number of key parameters, such as reservoir capacity, release, climate conditions, and so on. So we probably all know it is really difficult to add like a reservoir component within a hydrological model. And so in the literature, we have so many optimization models, simulation models, and for a data and a computational perspective, it's really difficult to make those run with the hydrological processes simultaneously. So now in the rest of few minutes, I'm going to share with you some kind of attempts from my own group. So last year we published a paper in Advances in Water Resources about a method, a data-based method to derive data-based reservoir operation models. And so I mean, if you want to know the specifics of the techniques, which is called hidden Markov decision tree, you can read the paper. And I just want to highlight the advantage of that approach is that it will allow us to use a limited number of inputs and derive a small number of representative operation models. And it could also allow us to catch the transitions, the dynamics, and most importantly, it could allow us to write operation rules in if-then rules. So in this way, we could write the operation rules explicitly. So right now, we are also following that work. We are also developing another component of the model, which is to identify the application conditions for different representative modules. So combining these two, we could have a generic model. So this is what it will look like. It's basically a decision tree, but you can see here for a particular reservoir, we could have 3 to 5, maybe 3 to 5 representative modules, and we have the application conditions under which condition a particular module should be used, and all this could be represented in this decision tree. And eventually, we could write if-then rules to simulate a reservoir operation under different conditions. So we got data from USACE, USBR. So I have not noticed the data Stacey just talked about. So maybe that would provide anyway even more data for us. But anyway, we have collected data for over 500 reservoirs in the continental United States and with different operation purpose. And so the good thing is that for all this, for over 500 levels, 500 reservoirs, we could apply this generic model to define a small number of representative modules, and so with relatively good accuracy. So what we want to do next, if we could not do it by ourselves, and we hope someone, sorry, I don't know why it does not. Oh, okay. Sorry. Yeah, that's my last slide. So this slide basically we just show with this data-driven generic reservoir models, how could we? There might be good opportunity for us to write reservoir operation rules inside a hydrological model. And so because they using the data-driven models I just talked about, we don't, I mean, the input, we don't need to have so many inputs. We just need to need the hydrological component to provide us the inflow, and we can estimate the storage based on mass balance, and we could have a few other climate-based inputs. And also we have explicit if-then rules to apply a particular module for particular condition. So hopefully, I mean, we hope we could publish this database and the generic data-driven models for 500 reservoirs pretty soon, and then hopefully some group can take up this and add and link that with a regional hydrological model. Thank you.
Thank you, Professor Kai. Our next speaker is Dr. Sankar Arumugam. He is a professor in the Department of Civil Construction and Environmental Engineering at NC State University. And I had the good fortune to have him as my PhD advisor at NC State. Dr. Arumugam studies the interface of climate and water management, and he focuses on large-scale hydroclimatology. So with that, I will turn it over to Sankar.
Okay, let me, so Ximing, can you stop sharing?
I think I already did, right? Sorry, okay, wait. Sorry. Oh, yeah, okay, good. Sorry. No, I start.
Yeah, thanks Sudarshana for putting together this nice seminar series, and also the idea of hydrologic connectivity. I feel that it started from, is it, you guys are seeing it fine or no?
Yes.
Okay.
Yes.
Okay, thanks. Yeah. So, so the idea of hydrologic connectivity, it started from the USGS Power Center first meeting that we had with Stacey, and then we contacted David Blodgett, and Sudarshana worked on this one. And so just to recap here, the idea that we are trying to present through this Cyberseminar series. So before this panel, we had 4 talks, and Kyle and David Blodgett, they basically focused on the core efforts and challenges in developing the digital hydrology connectivity. Kyle focused more on the importance of developing the registry. David focused more on the data formalism and also some of the challenges in developing the digital hydrology connectivity. And I will also mention some of those things towards the end of my short presentation. And Sudarshana and Mike Johnson, they presented the application of digital hydrology connectivity for actual infrastructure management. Sudarshana focused on the reservoir streamgage connectivity, and Mike focused on the flood forecasting aspects through the urban flooding open knowledge network. And so in today's panel, of course, you guys must have heard what the ongoing initiatives within USGS and CUAHSI, and Ximing, presented his idea, his paper on the how we can use a data-driven model that can be incorporated within the hydrologic model, and for that you need the hydrologic connectivity. So the key point why digital hydrology connectivity is needed. I mean, the thing is that the knowledge already exists. So what we do not have is that, I mean, most of the reservoir operators, they know that which is the upstream gauge that they need to look into. So the knowledge exists. What we do not have is that knowledge is not available in the form of digital information, so that we can have a national scale inventory that provides a basis for connecting reservoir or any infrastructure with upstream stream gauge, so that hydrologic information can be linked to infrastructure risk. So what I'm going to discuss today is more on, we can make this one more relevant by relating the digital hydrology connectivity to infrastructure risk and vulnerability. And these are very important, particularly during extremes, floods and droughts. And also it is important in the context of modeling some of the activities that Ximing mentioned, which is primarily trying to incorporate reservoir modeling or any infrastructure modeling, if it is appropriate, within the land surface models or any hydrologic models. So just to picking up on what Sudarshana did as part of her presentation and as part of her work recon. So basically, reservoir and stream gauges, we developed a connectivity for the entire Colorado River Basin, both upper and lower Colorado Basin. And I think she's working on extending this one at the CON-US scale. One important point on that paper is that this digital hydrology connectivity is not delineation of the watershed. It's basically beyond that. It's trying to provide the connectivity of the tree structure, that is the upstream and downstream, that the parent-child relationship for each entity that we are looking within the hydrologic network and its connection with the infrastructure. In that case, she focused on the reservoir. So I think that's a very important point. And moving from that, I think there is potential for now using this one for stream flow forecasting for ungauged basins. For example, you can take national water models. I mean, national water model, it gives forecast for any given location, but on the other hand, all physical model forecasts require post-processing. If we want to do that, we want to look at the upstream stream gauge information and downstream stream gauge information along with the basin characteristics in terms of post-processing these stream flow forecasts. And Chichi, as part of the CUAHSI project, is working in our group in developing this connectivity so that we improve the forecast for not only for gauged basins, but also for ungauged basins. And the third bullet, Ximing already mentioned, it is basically incorporating reservoir and stream flow into land surface models. And you can kind of consider this as a parameterization. I mean, land surface models or watershed models have parameterization. The same thing, reservoir models can be incorporated into watershed model as a way to parameterize the stream flow for controlled releases for estimating these things. For these things, we need the digital hydrology connectivity. And other potential extension that we can think about here is primarily, I mean, if reservoirs, why not, all power plants, I mean, like thermal, nuclear, run of the river power plants, and the thermal and nuclear, they need intake water, they need the location for the water intake. Particularly, this is a useful information they need to look at during the droughts. I mean, in terms of whether it is going to be below that, and also wastewater treatment plants, they need to discharge according to the inflow conditions, and water distribution system that is primarily requiring information on how the reliability of the water distribution system from rivers and reservoirs can be mapped into. And within the UFOKN project, we are also trying to link these connectivity, digital hydrology connectivity, to transportation networks. Like, for example, bridges, and other infrastructure that we want to connect with, so that the flood forecast, the stream flow forecast, can be appropriately converted into inundation forecast. The other aspect I think that requires attention here is the interbasin transfer. I think most of the archives, they go all the way back to 80s, and there is a recent nice paper, Dixon and Zombach, they try to address some of those issues that can be also linked in the context of digital hydrology connectivity. More importantly, I think once we know that, then we can try to provide boundary conditions for urban flood models, and this can help in providing information in the context of urban, not just for river reaches alone. The other aspect that I want to, so these things are potential opportunities, and all the speakers mentioned the challenges here too. So, for example, David Blodgett, he mentioned some of the challenges in terms of developing this hydrology connectivity, broken streamlines and stream networks. And these problems are much more when we enter into man-made landscape, like, for example, culverts and other landscape. I mean, the more the man-made influence, the connectivity is going to be disrupted a lot more. And streamlines and networks in urban catchments is much more challenging because it is difficult and there is no unified database exists. And I think as part of the UFOKN Urban Flooding Open Knowledge Network project, Venkatesh Marwadi from Purdue, he's working on trying to develop an inventory of HECRAS, and these models will require the corresponding hydrology connectivity in providing the boundary conditions. And similarly, the stream flow forecasts need to be converted into inundation forecasts, because finally, stream flow forecasts are relevant for reservoirs, but in terms of infrastructure vulnerability and risk, inundation forecast is the most important thing. And there are a lot of opportunities here in both rural and urban catchments. In urban, so obviously, if you have stage discharge relationships exist, it's relatively easier. But if not, perhaps something like hand method is possible, but that also has challenges in urban setting because the drainage locations and other things differ. And there are other issues also. I'll quickly wrap up some of those points. In infrastructure, like, for example, power plant may take water at a particular location, but on the other hand, the database may have the power plant location at a far off place. So the latitude and longitude may not connect with the streamline. So obviously we need to snap that one. So the challenges in snapping, there is a nice paper in Environmental Modeling and Software by Winslow and his group on how we should be careful in terms of not just looking at the centroid, but beyond that. So these are all real important issues in developing the hydrology connectivity. It cannot be just based on algorithm. Some quality control need to be made. And more importantly, I think once we have this hydrology connectivity with the infrastructure in a parent-child relationship, we can try to estimate or we can translate the hydrologic risk to infrastructure risk and vulnerability. Basically, we are looking at here a directed graph network with parent-child connectivity. And just my last point is that I think hydrological information is more useful as we take that information more relevant for infrastructure or other aspects where humans depend on it. I mean, modeling of virgin basins are good, but the more we incorporate these things in the context of human dependency in terms of using the infrastructure or other services, I think these things will be powerful. It's more like trying to use your navigation route while going from one location to another. The same thing is relevant in the context of infrastructure risk, and hydrological connectivity is the backbone for it. So with that, I'll stop and we can, I'll hand it over to Sudarshana.
Thank you, Sankar, for that recap and broad overview of the problem. It was really helpful. So we'll take questions from Q&A. In the meantime, I can start with my questions. One of the key assumptions in this digital hydroconnectivity development is particularly here in the US that we have a lot of ground-based observations, but locations where these observations may be limited, how can one develop this framework? And available satellite data, if available satellite data is there, can we use that to develop these hydroconnectivity? So I'll start with maybe Jerad, and we can, each of you can jump in with your response.
Yeah, so I think satellite data is certainly useful. It's generally two-dimensional. And in some cases, the hydroconnectivity needs to be three-dimensional. The other issue particularly relates to the one that Sankar mentioned about developed areas where you either have culverts or underground, streams that have been buried and so on. And so there's challenges with using satellite data. Certainly it's a good starting point in places where there is no information.
I'll just add on to that point. I think first, maybe we can think about reservoir and stream gauge before adding a lot more complexity. I think Global Hydrologic Network and also RAND, the Reservoir Global Database, they do have a decent amount of information, and we can use that one as a starting point to connect that. And the hydrologic connectivity with respect to stream gauge as well as the reservoirs, I think to that extent we can do that. But beyond that, like some of these things like culverts or other man-made structures like power plants. Like power plants, latitude and longitude, even within the US, I expect it to be far away from the location where the cooling water tower intake is located. So I think these things, we need certainly remote sensing data or other resources in terms of digging deep, and just an algorithm alone will not solve this problem.
I'll take the same question to Professor Kai, but I'll just add one more thing with that. You mentioned the SWOT model. So in general, what are the challenges or what are the things that we have to consider before combining this hydroconnectivity with physically based distributed models or in general Earth system models? Yeah.
Okay. So first of all, let me say a few words about the remote sensing data for reservoir observation. I haven't done any work myself, but Professor Ximing Cai at University of Texas A&M, and her group has done very extensive work of using remote sensing to estimate reservoir surface, reservoir storage in the world, and they also apply that data to derive the evaporation loss from the reservoir surface, and they also, I know they're even working on using the remote sensing data to derive the operation rules. I just want to add on that. So sorry for your second question. I'm not sure I really got the point. So for the work, for the two publications I just shared with you, they try to add some module inside the SWOT model, which could simulate the reservoir operation together with the hydrologic simulation. So I'm not sure. I mean, that's what I want to highlight, but I'm not sure that. Anyway, can you, or you, if you can clarify your question a bit? I'm sorry.
Yeah, like I'm wondering if there is any work going on that look at using this connectivity information for developing the mesh or the grid structure of the distributed models. Like if you know of any of such work.
I'm sorry, I don't, I'm not sure. I don't know the details on that. So.
I think maybe I'll add a little bit.
Mm-hmm.
I'll add a little bit on that. I think Hangi Lee from University of Houston, he has been working on incorporating reservoirs into land surface models. And Natalie Viosin from PNNL, she has been working on explicitly incorporating into a land surface model, or it can be done in the context of hydrologic model too. I think that's those are two things to my knowledge, and there are some papers on it too. One can look into, but what we have been working on is that to some extent, incorporating reservoirs into a land surface model or a hydrologic model can be also separate. I mean, in other words, it can be part of the post-processing, or it can be part of the routing. I'm of the belief that we don't need to incorporate everything into one model. It can be separate too. But to do that, we need to have the hydrologic connectivity. We need to have the upstream information and the downstream information on both stream flow and reservoirs so that it can be mapped into.
Thank you, Dr. Kai and Sankar. I'll go to Stacey for her response.
I don't really have much to add to the topic of remote sensing. I can tell you at USGS, we're looking at machine learning approaches to understanding reservoir operations, to try to process guided machine learning to try to understand reservoir operations. That's our first order attempt to try to solve the question of understanding in places where we don't have information about reservoirs. We're trying to do that. We are also trying to leverage where we have data to move to places where we don't. We are trying to also develop a more extensive water use data collection, water regulation, modeling capability as well, but that's going to take a longer, years-long process to build out. So in the interim, we're trying to find some solutions that can help us get there. Or perhaps I shouldn't say that, because I think the machine learning people I work with would not be pleased with that response, because that could be a real solution that would be built into our capacity that's not intended as a placeholder. That could actually be the solution we go with. So I shouldn't say, yeah, that process is better than machine learning. So yeah, anyways, that's my answer. Yeah, thanks.
So maybe
sure.
I'm not sure if I can add a little bit to that. So for, I would say, more than 50 years, we have tried physically based models. Like we have simulation, we have optimization. But it's always, I mean, it's really kind of challenging for us to use a model, a physically based model, to represent the comprehensive, realistic operation behaviors, right? So we sometimes say, all right, the reservoir manager wants to maximize hydropower generation, but maybe the real purpose is beyond that. So the problem is that we don't really understand the behaviors of all the institutional settings for the operation. We don't have much data for tracing that aspect. Unfortunately, our physically based model usually is because we don't understand that, we don't have data on that, we usually just ignore that. But if we have long-term data, so for example, we could find from US ACE or US BR, we could have found the daily operational data for over 30, 40, or even longer time. So that provides some hope to dig out the real operational rules, including not only the physical principles, but also the institutional aspects, the behavioral aspects, which are embedded in the data. So that I'm basically, I have some big hope for this machine learning data-based approach to understand reservoir operation. So
yeah, those are excellent points. Yeah, well said. Yeah.
Yeah, thank you for those comments. Those are really excellent points. So if we want to use this connectivity knowledge or river connectivity knowledge for extreme riverine floods, we all know the characteristics of floods are changing, climate change. So from that aspect, how do you see these connectivity, our knowledge of this connectivity will be helpful for understanding the floods and the effects of floods, flood hazard, and perhaps some mitigation processes? We can go to Stacey again, and that we can you can take that maybe.
Yeah, sure. When you were asking that question, I was trying to think about that. Like, I think my mind immediately went to like smaller structures, right? As floods, if floods get more extreme, right, smaller structures will probably be overtopped more, right? They'll become somewhat insignificant, one would think. So I guess I wonder, things might get more connected, right, in that way, maybe. I don't know what the hypothesis will be. I guess, you know, in some parts of the country, floods are increasing, other parts floods seem to be decreasing. We're publishing a paper right now. Hopefully we've resubmitted it to Water Resources Research, where we show the largest floods are perhaps not increasing. Some of the 10 largest floods haven't shown really much change over the last 50 years. So it's hard to know. So some of the larger dams, larger structures, I'm not sure. I don't know if I could comment on how that might affect connectivity. I think even if you look at large synthesis reports like the National Climate Assessment, it's still really unclear to make a broad characterization of how flooding is still inland flooding, I would say, is still very much like a mix of increases and decreases. So I don't know, I'm kind of searching for a good answer here, but I don't really have one. I think we're still at the point of trying to understand how floods are changing and what that effect will then have on infrastructure, like dams and things like that. I think we can say some things, and maybe Jerad can speak to, maybe he's involved in a lot of larger synthesis type work on these things and larger committees. To see if that maybe he doesn't want to speak on these things, but I'm just trying to think of more. So I just wonder, I'm just fiddling around here. Maybe others on the call might have thoughts. Maybe they're in larger synthesis conversations as well on this.
Sure. Yeah.
I will say that, okay, we think hydrologic extremes are changing at some level, at some rate. So from my perspective, the connectivity issues are greater or more value or more importance, and understanding impacts of drought and water availability, right? And so especially in the West, where we have water rights that don't exactly follow the upstream, downstream kind of typical flow of water. And then we have, offline uses of water and return flows and so on. And so understanding connectivity in the midst of lower flows and potentially changing water use will be and is really important, I think.
Maybe I'll take a crack at your question, Sudarshana. I think the connectivity is the key thing. I mean, it's not that, again, when I was mentioning that in the beginning, it is not that the knowledge doesn't exist. The key thing is that the knowledge doesn't exist digitally. Okay, so that's what makes it the challenge. And but it is important, once we have in digital form, then we can use that information to estimate the cascading risk and other things in the context of climate change. Like, for example, you can think of a stochastic, I mean, as I said earlier, I don't believe that all should be incorporated into a watershed model and we need to run everything together. But if we have the connectivity, we can use that one to, for example, develop a stochastic dynamic programming. Some of the earlier works like Benjamin Hobbs and others have done, they are really an example for this. But to do that at the national scale, you need to have this at the digital form, so that you can, cascade that risk from reservoirs to maybe to infrastructure, other infrastructure like power system and other things. So that level of connectivity, if you want, I think you need to have this available in digital form.
Yeah, maybe I can add a little bit. In terms of the connectivity with flooding, so we can find in many places the flood plains actually have been shrinking, or the actual area which could be used for flooding is evacuation is for flooding purpose is reduced than before. That's really because of the land use development. But based on some data analysis, particularly in Western United States, so we just found out that is pretty much related to the reservoir operation. So in Western United States, many reservoirs, not from medium to large reservoirs, were originally designed for water supply, or a large fraction of storage was used for water supply. But over time, with socio-economic development, the floodplain has been occupied, and then that pushed some requirement for flooding control. And then we found some kind of, we call it reallocation of the storage. So they reduce the storage for water supply or hydropower generation and add storage for flooding control. So that's it. Actually, we showed that in a paper published in WRL last year. So I mean, I don't know if this in general would reflect some connectivity change for flooding.
Yeah. Thank you for that response. That is excellent point. Yeah. And with the reallocation, this knowledge will be more useful for sure. And in one of the earlier talks, Kyle mentioned that he's working on a data portal where anybody can go, and Mike also mentioned his work where he's also working on a data portal where anybody can go and look at this connectivity specifically for urban flooding, etc. So we can take one more question from Q&A. We are almost, we just have time for one question. What is the state of the art? Modeling interaction and connectivity between groundwater and surface water at regional scale. I mean, if there is any work going on that incorporates groundwater.
So I answered this, I'm sorry, in the chat, I didn't realize, yeah, I just wanted to talk a little bit about USGS has a model GS flow that incorporates ModFlow and PRMS. USGS is currently in the process of working on I guess you could say a next generation integrated modeling capacity that will take the roots of our current modeling system and develop kind of a capacity that incorporates groundwater, surface water, water quality, sediment transport. So kind of all of the modeling capabilities that the USGS does into one integrated capacity. But right now, I would say that's the USGS capacity is GS flow. But to move outside of the USGS, I would say PARFlow is the other like kind of groundwater module that's incorporated into a surface water model. And Laura Condon is the contact that I know about. Laura, yeah, Laura would be great. You probably all know her on this call, but wonderful collaborative person. So yeah, that'd be the other person I would contact. I don't know if others have comments.
Jerad, do you want to come in with some last remarks?
I would say the same two models that Stacey said, and Reed Maxwell of Princeton is also Dr. PARFlow, so he would be a good contact.
Mm-hmm. Okay, we don't have any other questions. So thank you all for your time and this excellent panel. And all these will be available on CUAHSI's YouTube channel. So please share those videos. And if you have any question, the contact details will be there on CUAHSI website. Please contact the speakers. With that, thank you all for joining in. Bye-bye.
Thank you.
Thank you.
Thank you.
Bye.